So the last video was kind of a lot, right? We looked at these various indeterminate forms, and we saw that when we have the type where there's a variable in the base and the variable in an exponent, and we have to set up equations and introduce logs, they get really, really hard. The good news is those problems are way harder than anything we're going to do in this video, and quite a bit harder than most of the problems you'll see in this section. It is something I want you to be able to do, but I, your teacher, recognize how challenging it is. In this video, all I want to do is work through a bunch more examples, hopefully that are a lot more reasonable than the examples of the previous video. The examples I want to work through are things that we don't even need L'Hopital's rule for. However, they're examples where we've ran into indeterminate forms already, and I just want to make the point that because we had indeterminate forms, we could have used L'Hopital's rule. So maybe it'll get you more comfortable with L'Hopital's rule, solving these problems that really you don't even need L'Hopital's rule to solve. Let's consider the limit as x approaches infinity of 6x cubed minus 5x squared plus 7x plus 11 divided by 2x cubed plus x. In the previous section, the way we evaluated this limit is we recognize that the degree of the polynomial in the denominator is 3. So we'll divide each of the different terms by x cubed and then evaluate that limit. But suppose you didn't have that technique. Well, what you could do is recognize that as x gets infinitely large, the polynomial on the top gets infinitely large, and the polynomial down on the bottom gets infinitely large. So we have the infinity over infinity type, which means we can use L'Hopital's rule. L'Hopital's rule tells us that the limit of this indeterminate form is the same as the limit of the quotient of the derivatives. The limit as x approaches infinity of the derivative of the top divided by the derivative of the bottom. Since both the top and the bottom are polynomials, it's relatively easy to take those derivatives. The derivative up top is what? 18x squared minus 10x plus 7. And the derivative of the polynomial down on the bottom is 6x squared plus 1. It would be awesome if we could evaluate this limit, but we can't. It's still an indeterminate form because if you consider the behavior when all the x's approach infinity, the numerator approaches infinity and the denominator approaches infinity. So we still have this infinity over infinity indeterminate form. So we can use L'Hopital's rule again. We get the limit as x approaches infinity of the derivative of the top, still a polynomial, so it's still easy to take, 36x minus 10 divided by the derivative of the bottom, 12x. Again, you can try, although you might not even bother because you can kind of see the punchline. Try changing all the x's into infinities and you get an infinity over infinity case again. So we use L'Hopital's rule one more time. The derivative of the top now is just 36. The derivative of the bottom is 12. We consider the limit as x approaches infinity of 36 over 12, which is just the limit as x approaches infinity of 3. And since there's no x's in there at all, the limit is just going to be equal to 3. Because this limit equals 3, this limit equals 3, and this limit equals 3, the answer to the original question should just be equal to 3. Oh yeah, I remember that from the previous section when I instead thought about this as the limit as x approaches infinity of 6 minus 5 divided by x plus 7 over x squared plus 11 over x cubed divided by 2 plus 1 over x squared, dividing each of these 6 terms by x cubed. Using different limit laws, we figure out that this is 6 minus 0 plus 0 plus 0 divided by 2 plus 0. In other words, 6 divided by 2. In other words, 3. Yeah, the blue method might have been a little bit easier than the red method. The purpose of the red method is to give you a relatively easy L'Hopital's rule question and to make the observation that the results are consistent, that L'Hopital's rule does in fact work. Part B actually ends up getting really complicated. I thought this would work out nicely with L'Hopital's rule, but it turns out it doesn't. I want to show you how it doesn't work and then show you how you could solve the problem. But first I want to make the point that this gets way too ugly for it to ever be anything I would expect you to figure out. I do think it's interesting though. So first comment is we do have an indeterminate form. As the x value approaches negative infinity, the top approaches negative infinity. I think the bottom is going to approach negative infinity as well. So we have really negative infinity over negative infinity, this infinity over infinity indeterminate form. So we can use L'Hopital's rule. The original limit is equal to the limit of the derivative of the top, which nicely is just 7, divided by the derivative of the bottom, which gets really ugly because I end up having to use a chain rule in here. My outer function is the stuff raised up to the 1/3 power. So I bring that 1/3 down in front, and then I get 2x cubed plus x raised up to 1 less than the original exponent, so negative 2/3 in this case. But then I'm not done. I have to multiply that by the derivative of the inside function. The derivative of 2x cubed plus x is 6x squared plus 1. Using L'Hopital's rule, this original limit is equal to this limit. And it's cool that they're equal, but I think what you'll see is this limit down here is no easier to figure out. Because if I rewrite it a little bit, this term with the negative exponent, I can bring it up on top, and this 1/3, I can bring it up on top. leaving me with 21 times 2x cubed plus x raised up to the positive 2/3 power divided by 6x squared plus 1. The original limit is equal to this limit, but unfortunately this isn't a limit we can figure out either. Try evaluating the limit, you'll see that it's the infinity over infinity type, so you might be tempted to use L'Hopital's rule again, but if you do, I think you're going to kind of get stuck in this cycle. The denominator this time will simplify pretty nicely, but the numerator here is going to be a mess because we're going to have a chain rule. We'll bring the 2/3 instead of 1/3 down in front, and then we'll subtract 1 from the exponent, so the new exponent will be negative 1/3, but then we'll have to multiply by the derivative of the inside function, 6x squared plus 1. We'll end up with something that looks kind of like what we started with, where we have a polynomial divided by the cubed root of some polynomial. It doesn't get any simpler using L'Hopital's rule. For that reason, it would be an unfair question for me to ask you. I realized that when I tried to solve it making this video, but I didn't want to just delete it because there is a method for evaluating this limit. Rather than use L'Hopital's rule, the trick that you'll do will involve some algebraic manipulation. And really the key to it is to recognize that if you have something cubed raised up to the 1/3 power, that's just equal to that something. Exponents raised up to exponents, you multiply together the two exponents, and since 3 times 1/3 is just 1, x cubed to the 1/3 is just x to the first power, in other words, x. For this reason, I can rewrite this limit as the limit as x approaches negative infinity of, and then instead of writing the top as 7x plus 11, I can write the top as 7x plus 11 cubed raised up to the 1/3 power. Why would I want to do that? Well, because down in the denominator, where I'm taking the cubed root of 2x cubed plus x, the cubed root of something also means raise it to the 1/3 power. So I got a fraction where the top is being raised up to the 1/3 power and the bottom is being raised up to the 1/3 power. We could rewrite that as the quotient of the top and the bottom raised up to the 1/3 power. What I'm saying is this limit is equal to the limit as x approaches negative infinity of 7x plus 11 cubed divided by 2x cubed plus x, all raised up to the 1/3 power. What was causing trouble when we tried to use L'Hopital's rule was that we had the 1/3 kind of down on the bottom of the fraction, but not up on the top of the fraction. So that kind of put us into this little spiral where things never simplified. We've taken care of that by rewriting the top in an equivalent form that has this 1/3 power, so we can rewrite the entire fraction raised up to the 1/3 power. The reason that's beneficial stems all the way back to those limit laws that you learned long ago, or at least that I briefly introduced long ago. And what they say is when you're taking the limit of something raised up to an exponent, what you can do is take the limit of that something, get your answer, and then raise it up to an exponent. So really all I have to do is figure out the limit as x approaches negative infinity of 7x plus 11 cubed divided by 2x cubed plus x. And once I figure out that answer, raise that answer to the 1/3 power and I'll be done. So let's work inside the parentheses here. Let's just work on this box in red, maybe off to the side, and I'll remember that my answer is the box in red raised up to the 1/3 power. Can we evaluate the box in red? Well, no, it's an indeterminate form. Try changing all the x's into negative infinities, and you'll get the infinity over infinity type. So I can use L'Hopital's rule and say that the inside here, the stuff in red, is the limit as x approaches negative infinity of the derivative of the top, which would be 3 times 7x plus 11 squared times the derivative of 7x plus 11, which is just 7. That's the chain rule going on there. Divided by the derivative of the bottom, which will be 6x squared plus 1. Unfortunately, this is still an indeterminate form, so we'll use L'Hopital's rule again. It's still the infinity over infinity indeterminate form. Maybe I'll let you verify that on your own. If I rewrite the top as 21 times 7x plus 11 squared, then I can take the derivative of the top. The 21 is just a constant. The derivative of 7x plus 11 squared, I bring the 2 down in front. So I got 21 times 2, in other words 42, times 7x plus 11 to the first power, times another 7. And then down on the bottom, the derivative of 6x squared plus 1 is 12x. Maybe I can simplify this a little bit, keep the numbers a little bit smaller. 42 is 7 times 6. I can take that 6 and cancel it with the 6 down in the bottom. And then I'm left with just a 7 here and a 7 here. So I got 49 times 7x plus 11 divided by 2x. Good news is this is starting to get a little bit simpler. Bad news is it's still an indeterminate form, so I use L'Hopital's rule one more time. It's still the infinity over infinity indeterminate form. Take the derivative of the top. The derivative of the top would be 49 times the derivative of 7x plus 11, which is just 7, divided by the derivative of 2x, which is just 2. This is the limit as x approaches negative infinity of 343 divided by 2. What's the limit as x approaches negative infinity of 343 over 2? Well, there's no x's over here to approach negative infinity, so it's just equal to 343 divided by 2. So that's my answer? No, that's the answer to the limit in red here. The answer to the question would be that value in red raised up to the 1/3 power. So the answer to this question is 343 divided by 2 raised up to the 1/3 power. It's worth pointing out that you can simplify this. You can call this the cubed root of 343 divided by the cubed root of 2. And then maybe you'd recognize that the cubed root of 343 is equal to 7. So I get 7 divided by the cubed root of 2 as this limit. The reason I took it this far is because this might be something you recognize from a previous video when we evaluated this limit a much easier way than using L'Hopital's rule. A couple more quick examples. We did some work earlier in the class with removable discontinuities. Maybe you remember evaluating these limits? At this point, we knew nothing about derivatives because we evaluated these limits to figure out derivatives using the definition of the derivative. But if we already knew derivatives at this point, then we could have used L'Hopital's rule here. The limit as h approaches 0 of this expression, this is the 0 over 0 indeterminate form, because when h is approached 0, we get 9 minus 9, aka 0 on the top, and a 0 on the bottom. So I can use L'Hopital's rule, which tells me that this limit is the same as the limit as h approaches 0 of the derivative of the top, treating the h as a variable. Let's see, 3 squared is just a constant, so that goes away. I get 2 times 3 plus h raised up to the first power times the derivative of 3 plus h, which is just 1. So I get 2 times 3 plus h divided by the derivative of the bottom, which is just 1. The limit as h approaches 0 of 2 times 3 plus h divided by 1 is just 2 times 3 divided by 1. In other words, 6 divided by 1. In other words, 6. Previously, the way we evaluated this limit was by expanding out the numerator. We call it the limit as h approaches 0 of 9 plus 6h plus h squared minus 9 divided by h. And then we combine like terms, getting rid of the 9 and the negative 9 to get 6h plus h squared divided by h. And then we cancel out an h from the numerator and the denominator to make this 6 plus h. This was a limit we could evaluate. We can change all the h's into zeros, and we got 6 as our answer. Rather than doing the problem this way, had we known L'Hopital's rule way back then, we could have done the problem a little bit quicker. You're like, yeah, that saves a little bit of time, I guess, but this way in pink wasn't that bad. Right, but remember how hard it was when we had radical functions and rational functions? Up here, the trick we had to do was multiply by the conjugate, and down here we had to algebraically simplify to get rid of the fractions inside fractions. Those problems were really hard, but if we had known L'Hopital's rule then, we could have done these problems completely differently. We could have recognized that we have an indeterminate form. It's the 0 over 0 type if we evaluate this limit. So what we do is we take the derivative of the top and the derivative of the bottom. The derivative of our variable is just equal to 1. The derivative of the top, we have 2 terms. The derivative of the negative 2 is just 0, so that goes away. Taking the derivative of the square root of 4 plus h, think about it as 4 plus h raised up to the 1/2 power. So I get 1/2 times 4 plus h raised up to the negative 1/2 power times the derivative of 4 plus h, which is just 1. I can clean this up a little bit by rewriting it as the limit as h approaches 0 of 1 divided by 2 times 4 plus h to the positive 1/2 power. The nice thing about this expression is it's not an indeterminate form. We change all the h's into zeros, we get 1 divided by 2 times 4 plus 0 to the 1/2 power. 4 plus 0 is 4, 4 to the 1/2 power is 2, 1 divided by 2 times 2 is 1 divided by 4, which is what this limit evaluates to, using the more challenging methods that we learned earlier in the class. One last example, fractions inside fractions. This is again the 0 over 0 indeterminate form, because as all the h's get close to 0, the fractions up top both get close to 2/5, and 2/5 minus 2/5 is 0, and this h turns into a 0, so I can use L'Hopital's rule. When I use L'Hopital's rule, the derivative of the bottom is just a 1. The derivative of this 2/5 goes away. So really the only challenge is taking the derivative of 2 divided by 5 plus h. You could use the quotient rule there, but I think it's easier to think about it as the derivative of 2 times 5 plus h to the negative 1 power. Because then you can just leave the 2 alone as a coefficient and bring the negative 1 down in front, leaving the 5 plus h completely alone. My new exponent is negative 2, and I just have to remember to multiply by the derivative of 5 plus h, which is just equal to 1. So this derivative is negative 2 times 5 plus h to the negative 2 power. In other words, negative 2 divided by 5 plus h squared. So since I'm using L'Hopital's rule and I need to know the derivative of the top, I replace the top with negative 2 divided by 5 plus h squared. The nice thing about this is the limit as h approaches 0 is something that I can figure out. You change all the h's into zeros, and you get negative 2 divided by 5 squared, in other words, 25. Without doing all the challenging algebraic tricks that we did when we first learned this stuff, we can evaluate this limit using L'Hopital's rule. I think that's kind of cool.